Hello, everyone. Welcome to the IEEE Big Data Analytics tutorial series. This is Qiu Shi from Arizona State University. Today, we are honored to have Professor Thomas Overbye to talk about new developments in the visualization of wide area electric grid information with application to grid interconnection studies. This presentation discusses some of the new visualization techniques that are being deployed by the electric power industry. These include animation, contouring, time-varying graphs, geographic-based displays, image blending, and data aggregation techniques. The techniques are demonstrated using a variety of actual and synthetic electric grids, including some studies focused on the interconnection of large-scale electric grids. This talk will be around 90 minutes long. At the end of this talk, there will be a Q&A section. During the talk, if you have any questions, please feel free to send them to me through the chat box of Zoom. Now, I will give the speaker to Professor Yang Wang. He will briefly introduce Professor Overbye.
Thank you, Qiu Shi. On behalf of the Big Data Subcommittee, I would like to thank Professor Tom Overbye for this opportunity. For the development of big data, one important part is we need somebody who is so knowledgeable about the past and also so knowledgeable about what is happening in the future. So Professor Tom Overbye is a professor and the foundation chair in the Department of Electrical Computer Engineering, Texas A&M. Before joining Texas A&M in 2017, he was a Fox Family Professor at UIUC. He got his bachelor, master, and PhD degrees all from University of Wisconsin Madison. Before starting his academia career, he was employed with Madison Gas and Electric Company. He is the original developer of Power Word Simulator, co-founder of Power Word Corporation, and the author of a widely used power system analysis and design book. He was the recipient of University of Wisconsin-Madison College of Engineering Distinguished Achievement Award, the IEEE Power and Energy Society Outstanding Power Engineering Educator Award, and is a member of the U.S. National Academy of Engineering. With that, we really look into the information that we can absorb today and develop new tools for big data community. Thank you, Professor Overbye.
Okay, thank you. And thanks to the committee for this opportunity to talk to everybody today. I really appreciate it. I wish we could be gathering, in the general meeting, but I guess that's not going to occur this summer. I'd like to start with some acknowledgments. The work I'm going to present here is supported by many different entities, some of which are listed there. The slides also contain contributions from many people, including my students, postdocs, staff, and colleagues. And I will say one of the fun things about being a faculty member is the chance to work with so many great students and postdocs and staff and colleagues. And I really appreciate that part of the job. The sad part is, your students graduate and they move on. That's good for them. But of course, it's sad for us to lose them, but good overall, I suppose. The slides in the associated papers I'm going to talk about are available on the website given there. So if you want to download them, I think our admin person just put the slides up already so you can get access to them there. The work I'm going to show here is general visualization techniques, but people will always ask, well, what did you do it in? And the answer is we did the simulations and visualizations using Power World Simulator version 22. And you get a free version of it at that website, but I'll be just presenting general techniques here that could be developed in any software. Okay, starting out, I like to Am I muted? No. I said I was unmuted, but okay, I'd like to start out on a positive note. And this is a very positive presentation all the way through, but I think it's a great time to be in the electric power field. Lots of new developments going on. Wonderful time to be a student in this field. And there's lots of good things going on. But there's also, with all these changes, potential stress on the grid, and that stress can have an impact, and it's a challenge from a planning perspective, and it can be a challenge from an operations perspective. So I think we need to provide the best visualization techniques that we can, and I hope this presentation helps somewhat in that regard. So the goal of the presentation is to give some wide area visualizations. I try to demonstrate these techniques on large systems, so you'll see that coming up. The goal is to provide ways in which we can take data that might be coming from measurements in the system or from application software and turn it into something that can be used to make decisions. Now, the focus here is more on visualizations for engineers as opposed to operators, just because I'm an engineer, so I kind of focus on engineering tasks, but some of them certainly could be applicable in the control room as well. Before getting into the presentation, I did want to give a brief ad for the North American Power Symposium. We'll be hosting it here at Texas A&M in November. It will be a live in-person event. We hope everybody can join us. The weather in November here should be great. Papers are due in about a month. With the paper submission website just going live yesterday. So I hope all can join us for this, and it'll be nice to see everybody in person again. Okay, so what are some examples of power system big data? For this community, people mostly know that we generate lots of data that can come from sensors in the field, with the phasor measurement units, of course, one of the more common ones now. But it can also come from studies that you do in a planning context. The motivation for this, which I'll talk about on the next slide, was a large study that we were doing, which was generating lots of data, and we were having a challenge figuring out what was going on. So some of the work presented here was developed as a result of that. In particular, the study that we looked at was funded through Southwest Power Pool with PCIRC. Well, it was funded by SPP through PCIRC. They wanted us to look at a potential interconnection, AC interconnection of the eastern and western grids, and we did that. What we did is we took a full Eastern Interconnect model and then a full WECC model, joined them together. We had a model then that had about 110,000 buses in it, 244 different dynamic models, 48,000 model instances in 194,000 states. We ran primarily stability simulations, so we did some static analysis as well. And it generated a lot of data. We would run simulations. Sometimes they were very short, 10, 15 seconds for fault studies. Sometimes they would go up to 6 minutes to look at the longer term system response. And we had a major challenge in figuring out what was going on with all this data. So it helped spur us on to develop some of the visualization techniques that I'll be presenting here today. In particular, for that project, what we did is we joined the two grids at 9 locations where the grids are already pretty close geographically. These range from Montana down to New Mexico, and they had voltages that ranged from 345 kV down to 161 kV. With the 9 interconnections, we were actually able to get very good stability response on the grid. In particular, the West seemed to respond much better to frequency disturbances in the sense that the frequency would recover faster when they were interconnected with the East. That graph on the bottom right, the thick lines show the frequency variation at several buses when the grids are connected, and the thin lines show the frequency variation at the same buses when the grids are simulated being apart. And you can see that the time scale on this simulation was 30 seconds. You can see that the frequency recovered much quicker. And that's not surprising because when you interconnect the grids AC, if you have a disturbance in the west, a lot of the makeup power flows over from the east. And actually that was the most constraining part of this study, was that anytime you had a west disturbance, the power flow had to come in from the, or about 80% of the makeup power would come in from the east, at least over the first 30 seconds before the automatic generation control could respond. So the takeaway on this study was the cost to interconnect AC would be relatively low, and such an interconnection certainly merits further study. Okay, but the talk here isn't about that study, but it was a major motivator for some of the newer work that I'll be presenting here. Focusing more on visualization software design, one of the key issues that has to be addressed when you're doing this is to say what is the desired task that you want to accomplish, and then the visualizations would be tailored for that task. The needs in real-time operations could be quite different from what's needed in planning. And in planning or operational planning, the needs could be quite different depending upon what you would like to accomplish. For example, if you're running thousands of contingencies or stability simulations, it might be that you just want to know, is it stable or not, or did it meet some criteria? So it's a yes, no question. So you really don't need to know a lot of the details. In contrast, in the study simulation that we were doing, where we were interconnecting two large grids and we were looking for hidden problems, we really had to dive into the nitty-gritty of what was going on with the response. So it required a lot of what we'd call situational awareness of our study to really know what was going on. Overall, the software should help humans make more complex decisions. It should alleviate our weaknesses, and our weaknesses, you know, we don't add up numbers fast, but computers are really good at that. And it should enhance our capability. You know, we've got, as humans, lots of great capabilities, certainly in terms of interpreting results from studies. Okay, there's a number of different books that, if you're interested in information visualization, that you can look at. I found the one by Colin Ware to be quite helpful. It's now in its 4th edition. There's books by Edward Tufte. Those are getting a little dated now with the last one from 2006, but they're still useful books. And then there's other ones that you can find to help in software design for visualization. In giving any visualization talk, I do like to include a caution. This actually comes from Edward Tufte's book. Just because information can be shown graphically doesn't mean that it should be shown graphically. A lot of times, particularly if you're trying to show a small amount of data, text-based approaches are best. If you try to create a 3D plot, and Tufte calls that image there the worst graphic ever, where they're taking essentially 5 pieces of information and visualizing it in some 3D sense and using 4 different colors. And the top image is kind of a mirror image of the bottom image. It's just confusing. Try to do it as simply as possible. There was a 1994 EPRA report that was quite useful in this area, and they gave 3 useful design criteria, which was try to use a natural encoding of information, task-specific graphics, so you know what you're trying to accomplish, and then don't use gratuitous graphics just for the fun of it. Visualizations also do not exist in a vacuum, and you need to take into account the prior experience of the users. This is a real challenge as we do human factors testing on some of these newer visualizations, because if you're developing newer visualizations, people aren't as familiar with them. So it might be a better way to do it, all things considered, or all things being equal, but oftentimes all things are not equal. And the classic example is the keyboard that probably many of you have in front of you right now, which is a QWERTY keyboard. That was designed in the 1870s. Some people say it was designed the way it was to prevent mechanical problems, but we still use it today, even though there are probably much better ways to design keyboards for faster typing, but it's something that we're all familiar with. The other issue is visualizations oftentimes are based on something that is familiar. Oftentimes it was familiar before it was visualized on a computer. And increasingly things that we see on the computers like analog clocks or gauges or sliders or buttons, or sometimes a file folder, we're no longer encountering in any context other than on a computer. You know, clocks are you seldom see an analog clock anymore. You seldom see a file cabinet with files, but yet we still use kind of these metaphors for how we do our visualizations. So that's something to keep in mind. Before getting into the detailed results, I want to say that the challenge with visualization and actual power system data and models is with visualizations, we are trying to show people what is going on. We're trying to be as clear as possible, and we run the risk with actual grid results of being too clear and disclosing things that should not be disclosed. Here in the United States, a lot of information about the actual power grid models is called critical energy electricity infrastructure information, or what we call CEII, and that prevents it from being freely shared with other researchers, and sometimes even presenting results can be difficult. We ran into this with our East-West interconnect study because we were definitely getting very technical engineering results, and we could not show in a public forum all of our results. What we have been doing is to create synthetic electric grids or fictional grids that mimic the characteristics of the actual grid, but are synthetic, fictional, what my colleagues at University of Wisconsin like to say, realistic but not real. Sometimes I'll call them fiction, but hopefully it's good fiction. Kudos to the US ARPA-E for funding work over the last 6 years in this area. A lot of progress has gone on. And I'll be using synthetic grids throughout this presentation, which makes everything in it publicly available. The synthetic grids are models of an electric grid that doesn't represent any actual system. This can be a non-geographic grid, and the one on the left is the 5-bus system that I ran into when I was a student using the Stevenson book. I used the 1982 edition, but that 5-bus system probably dated to the first edition from 1955. Some synthetic grids, like the one on the right, are one that I made up in the 90s that is pseudo-geographic in that I took an electric grid and I put it on a hand-drawn map that sort of looked like Wisconsin, Illinois, Minnesota, Iowa, and suddenly it was pseudo-geographic, and people understood that I was trying to say something about a grid that resembled, to some extent, the grid in that part of the world. Since then, we have gone quite a bit further, we being the entire industry, because a lot of people have been working on developing these synthetic grids. There's now synthetic grids available up to 82,000 buses that cover the continental US. And that's one that we use partially in the East-West Interconnect study to present some of the results, and what I'll be using a lot from today. I will say for the actual electric grid, over the last maybe 5-6 years, there has been a vast increase of the amount of geographic information available about the actual grid. Some of this was driven by the geomagnetic disturbance studies, GMD impact studies, where people needed to know where their substations are. So increasingly, power flow models come with geographic coordinates for at least the substations. This is an example of a 2,000 bus synthetic grid that we made up as part of our ARPA-E project. It covers a footprint that corresponds to the ERCOT portion of the grid, the ERCOT is the Electric Reliability Council of Texas. The grid was designed to serve a load that is the same as the Texas load, but and it actually has generation that matches where the generation is in Texas, but then the entire transmission system is fictional. And to emphasize this, we designed it using a grid that's different from the actual grid. It was designed with a 500, 230, 161, 115 kV grid, whereas the actual grid in Texas is a 345, 138 kV grid. But this system is used a lot. We use it here at Texas A&M a lot in education, but we also use it a lot in research. And I know it's being widely used out in the industry. This one here is a little bit larger system. It's a 82,000 bus synthetic grid, where what we did is we took the Texas 2K, then we designed one for the West that had 10,000 buses, covered the US portion of the WCC interconnect. And then we designed one for the East that covered the Eastern part, or the US part of the Eastern interconnect, put them together and had an 82,000 bus system. The different colors indicate the different voltages, with green being 765 kV, orange 500, red 345, blue 230. In developing this grid, we deliberately used different voltages, just like we did with Texas. Some of our more recent synthetic grids, we've relaxed that. We actually designed synthetic grids now that use the same voltage levels. For example, we now have a 7,000 bus grid that covers Texas that has a 345 kV, 138 kV transmission system, but all of it is still fictional. Okay, so in visualization, what we are helping, hopefully, is people make decisions. So the goal is to help people make better decisions. So when we talk about visualizations, usually we're trying to figure out what decision is somebody trying to make. And you start at the most raw level, which is data. And then hopefully as you move up, your data becomes information, it becomes knowledge, and it becomes understanding or wisdom at the top. So hopefully as we're taking the raw information, we're providing more understanding, you might even say wisdom at the top. We ran into this as we do these stability studies on the East-West interconnection study. We do a study and you'd have a lot of data. You know, you can think about 110,000 buses, you've got frequencies, you've got voltages. We might be storing it at 30 times a second or even more. A lot of data that you have to process, and then you want to know, well, what is the system really doing? And at the end of the day, you kind of get some insight. And some of the insight might be, hey, that generator over in Manitoba is oscillating. We need to do something associated with it. Some of it could be as you do a Western disturbance, a lot of power goes through the mid part of the country, and you might have voltage issues associated with that. What do you do about that? So that was the goal of our visualization, something that we try to keep in mind in creating all these visualizations. Understanding the entire process is crucial when you do this. Ultimately, as we create visualizations or create visualization approaches, we want to be as flexible as possible because people are going to be asking different questions. So you want to have visualizations that can be customized for the question of issue or the issue that you're trying to deal with. And then you have to think through the whole process and look and say, okay, well, what is the information access cost? How long does it take me to figure out what that voltage is? So I might see a voltage in a grid. Maybe I don't even know much about the grid. When we started out on the East-West study, we had 110,000 buses across the whole of North America, and a lot of them, we didn't even know where they were. So we wanted to know where they were. How is the information going to be used? Is it going to be shared? Is it raw data? Is it derived data? Ultimately, what is the task that you want to accomplish? So this is all part of the design process. sometimes the best way to show information is to use tabular displays, you know, where you're looking at a set of records. And this is an example where the records are, I believe this is showing buses, and I might want to know the bus's number, its name, what area it's in, what's its voltage, what's its nominal voltage, you know, and I can just show it in a tabular form. This can be very effective, particularly if you have interactive features like sorting and filtering and drill down. It's something that I use all the time. Another general issue to deal with in information visualization is the use of color. You know, color is something that most of us are not colorblind, but some people are colorblind. If you're not colorblind or not fully colorblind, you use color a lot to differentiate all sorts of different things. So we make use of color, but as you make use of color, you have to be careful not to overdo it. The book by Colin Ware is a great resource if you're looking at how should you use color in visualizations. He has a lot of information in there. For example, you usually don't want to use more than 10 colors if coding a particular value is important. Also, color sequences are very important. How you set up your sequence, like I just saw an example of a sequence. It was actually in a Facebook post where the color sequence went from essentially black infrared to kind of black ultraviolet. So the values at the end of the color mapping, which was more a spectrum mapping, kind of looked the same because they were pretty dark. So you got to be careful with that. Okay, graphs are a great way to show information. We use graphs all the time. I like graphs. We're getting a little echo here. Graphs are a great way to show information, but you have to be careful and you have to figure out what do you want to show that, what information do you want to show? The graph on the left is one where maybe I want to show this particular response at 10 buses. This is frequency over 30 seconds. And I'm using a small enough number of colors that I could put a key on there and I could uniquely identify each curve to a particular location. The one on the right is one that we did a lot in our studies where we wanted to know, is our system settling down? How is it settling down? Are there any outlier behaviors? So we would take, say, 40,000 bus frequencies and plot them all out and look at them. And of course, you're not seeing individual values there. And of that graph on the right is showing 40,000 signals. There's a lot that are hidden. You can't see them, but you do get a feel for the overall response of the system, and you know whether you're settling down or not. This is an example from our East-West study where we wanted to then differentiate and say, okay, how's the West behaving relative to the East? And at first we said, well, let's make all the West red and all the East blue. And that's good. The West for this disturbance had a higher response. But, you know, most of the blue is then hidden. So then we thought, well, let's go ahead and set up a separate graph for the East and a separate graph for the West. Which one you're going to use depends upon your need. And they can both be useful ways to show information, either combining them all together using different colors or separating some out. A visualization that we commonly use in the electric power community is Onelines. Onelines can be very effective for showing what is going on at a substation or kind of a local region. Of course, in a Oneline, we're drawing our three-phase system using a single wire or single line, so hence the Oneline or single line. And they're used all the time in an EMS system for control, quite useful for educational applications, but they get cumbersome as you get to showing a lot of information. Some general visualization techniques that can be leveraged are mentioned in the Colin Ware book, which again, I find an extremely useful resource. One is this concept of preattentive processing. Preattentive processing is making information so it stands out. This is an example from the information visualization book of different information encodings that are preattentively processed. That means you don't really have to think about it. One stands out from the other. And the top one is orientation. If all of your lines are going one direction and one is kind of tilted, you'll immediately see it. If you've got all circles and one is shaped differently, it'll stand out. If it's mostly green and one is red, it'll stand out. If they're mostly small, one's large, it'll stand out. So these are different ways that you can preattentively process information. The only two on this graph that are not preattentively processed are in the bottom right, and that's junctures not a preattentively processed, and parallelism. So if I said which ones are not parallel versus parallel, you'd have to think about it some. This is an example how we use color on some of our small grids. If we want to highlight, hey, which transmission lines are overloaded, we'll increase their size and we'll change their color. Or if we want to highlight which lines are open, we'll increase the symbol. In this case, a pie chart is showing the percentage loading at the transmission line, and we'll change its color or I guess what we show in it. Another one is the concept of detecting patterns. This is Gestalt, which is German for patterns, laws. There's different laws that you can take advantage of. Again, the information visualization book is quite helpful on this. Things like, how do we perceive rows? How do we perceive columns? I take a bunch of dots, and in the upper left, you perceive them as rows. I take that same bunch of dots, change them a little bit, and you perceive them as colors. I show you in the middle here six black circles, and we naturally think of them as two groups. If I draw lines between things, it turns out that that line is giving a connectedness, and that is stronger than proximity, shape, or color. So, you know, if you look at the upper right image there, the red and the black on the top look like they're connected together, even though they're different in terms of color, but that line gives you that connectedness. And this is something that we take advantage of all the time with the electric grid, because we draw one lines where we're connecting buses by lines. Patterns in motion can be very effective for showing a relationship between data. If I were showing this as a live presentation in person, as opposed to using an internet connection, I would show you an animation to show how we can use animation to make information pop out and give you a sense of connectedness. In a grid like this here, which is a 42 bus grid, some of the buses that are quite far apart on the one line are connected by transmission lines. And if you've got a flowing animation between them, it helps to highlight that connectedness. But of course, if you put too much motion on a display, you're just going to distract people. One technique that we've used a lot is color contouring, or what's more formally called scattered data interpolation. If you have a bunch of data and you want to show patterns between that data, spatially, I should say spatial data. If you have a bunch of spatial data and you want to show patterns, if you put a contour on, particularly if you do coloring, suddenly you can start to see patterns in the data. For example, this is a visualization where we're contouring the bus voltage magnitude with a red-blue color mapping. And it's pretty clear that part of the system is at a lower voltage, part of the system is at a higher voltage. It's 40, and what I'm contouring here are ultimately 42 data points. So it's not a lot of information, but the contour helps to immediately make sense of it. Of course, contouring only works if there really are these patterns. If each one of those bus voltages was not correlated with the voltage of its neighbors, it would not be an effective technique to do. When you take scattered data and you interpolate it, you have to use an algorithm for interpolating it. One that we've used a lot of is Shepard's algorithm. Another approach that we've recently been using because it's faster is to do a Delaunay triangulation and then color our contours based upon the Delaunay, underlying Delaunay triangulation. That's a similar visualization. It's the same data as the previous image. It's just we're using a different interpolation algorithm. This one's faster. And then there's a question of what color mapping do I use? Slide 33, I'm using a discrete color mapping where you can kind of see the different lines there because I think I have like a 21 step color mapping. This is more of a continuous color mapping. It's a spectrum color mapping, which isn't really the best in a lot of situations, but it's one that is commonly used. So it's the same data, it just appears a little bit different. You do want to be careful that if you use a color mapping for your contour and you use colors in the one line itself, you got to be careful because if I put a red pie chart to show a line that's overloaded on top of a red contour, it pretty much blends in. So picking the right color sequences is really an important consideration in doing this. Otherwise, your contour can very effectively camouflage other information. Okay, some general thoughts on visualization. They're very helpful, but a lot of times we just can't show all the data. So we need to take advantage of more interactive ways to do it. So the next couple slides are going to show some interactive ways for showing data. One that we use a lot of, we're calling geographic data views or GDVs. That idea of a GDV is to, if you have an electric grid that's got embedded geographic information, which is now quite common, we can use that embedded information to dynamically draw displays. So we don't have to put the images on the one line ahead of time. We can dynamically assign them. And then because there's a dynamic linking between what's on the one line and the underlying data set, usually we'll use what we call a style so that we group them all together. And then we can use a consistent way to customize how the information appears. For example, we might customize all the sizes based upon some piece of information. If you then have dynamic linking and drill down capabilities, this can be quite useful. For example, on the next slide here, if I took that 82 bus or 82K grid, which is shown in the bottom right, and I wanted to give you a feel for what are the different area loadings. In this case is divided into something like 100 areas. If I put a GDV based on, for the area, based on the geographic location of the buses in that area, then I can draw it on the display. For example, in Wisconsin, I took all the buses that were in the Wisconsin area and I averaged their geo coordinates, and it's somewhere in central Wisconsin. So I draw the image there. Then I put a consistent sizing. Here I size the images based upon how much generation is in that area. And then I did a consistent coloring on it. And I colored the images based upon whether it's importing or exporting power. And suddenly I take 82,000 buses, which are pretty hard to interpolate or to understand. And I give you a feel for how my system is divided, how the power transfers are going in the system, at least to some extent. This can be done on all different objects. We commonly do it on areas and substations, sometimes on buses, sometimes on generators, sometimes on switch shunts. This takes the Texas 2000 bus case. It's got something like 1,500 substations in it. What I did is I put a GDV on the display for each one of the substations, and I sized it based upon how much power is going through that substation. and then I colored it based on its generation. Now, this image helps make sense of the grid, but you can see that a lot of those GDVs are overlapping one another. So having some sort of layout algorithm will help as well, something that I'll show in, I think, 2 or 3 slides. This is an example of the GDV for the 82,000 bus system, where I'm showing, I think, the 40,000 substation GDVs. What I did is I colored it based upon whether the substation had net injection of power or net withdrawal of power. Of course, if it's got net injection, it's a generation substation. If it's got net withdrawal, it's going to be a load substation. You know, here you can kind of see the load, the generation load patterns here, although the load substations tend to be pretty small and dispersed because the load is small and dispersed. Slide 40 gives an example of using GDVs, and then we applied a layout algorithm, a pretty simple force-based layout algorithm to move them around, to spread them out. Here I'm coloring each one of my GDVs based on its percent reactive power. If it is close to its high reactive power limit, I colored it red. If it's close to its low reactive power limit, the negative reactive power limit, I colored it blue. I think I set the scale there. I used a deadband scale. So for the ones that were less than 80% reactive power output and above minus 80%, I colored them white. And then the size is based upon the generation at the substation. Pretty quickly from this image, you can take those 82,000 buses, and of course, not all of them are generation, but a lot of them have generation, and get a feel for the reactive power loading on the system. In particular, we've got a lot of generators that are either at their high or low reactive power limits. That's not how the grid is actually operated, but that's how power flows often converge. The point of this slide isn't to say whether the power flow algorithm is doing a good job or not in setting the generator reactive power outputs. The point is that you can see it very readily here. This is just another example GDV where we've been working on developing some new synthetic grids using EIA 860 data, which gives information about all the US generators as public information. And what we wanted to know was kind of how does it look and what are the different fuel types. So what I did is I set up a simple GDV with all the generator information and then colored it based upon its fuel type. And it's pretty quick to do, and it gives you a nice feel for where the different generator sources are in the country. Red is nuclear, black is coal, brown is natural gas, and green is wind, and yellow is solar. These GDVs can apply to all sorts of different objects. On our study that we were doing, we had a lot of contingency data. We had 250,000 contingencies that we were considering, and we would do contingency runs. We kind of wanted to figure out what the results were showing. So we'd create GDVs, and then we would dynamically size the GDVs based upon whether a contingency solved or had violations or things like that. So the scatter plot on the right is showing each of those 250,000 contingencies, where we just place the dot based upon where the average of the contingency was. If it's opening a line, we just average the from and to bus and put the dot there. Of course, you can't really effectively show 250,000 contingencies, but if you do a contingency run and 1,000 of them have problems, you can visualize that. Or the image on the left is showing some remedial action scheme information. Again, you can use geographic information to kind of put an image on there, and then you link it, and then you can get lots of information through drill down capabilities. Okay, one technique that one of my grad students developed is called pseudo-geographic mosaic displays. This was motivated by the fact that with a GDV display, a lot of times we're not effectively using all of the screen space. So we thought about, well, what if we dynamically sized our images to use more of the screen space? So with this approach, what we do is we allow people to specify how much of the screen space they want to use, and then we lay out our GDVs to take up that much screen space. The one on the left is where it's the percentages there, the percentage transition from the initial image to the final image, whereas the final image is using all the display space essentially, and the first image is using a very small part of the display space. We set up GIFs that kind of allow you to go between 0 to 100%. It's kind of interesting to see. They're certainly useful, and they're most useful if you can dynamically transition between 0% and 100%. So it's a way to make information stand out. This is an example that Texas 2000 bus one that I showed before, where the size is proportional to substation megawatt throughput and the color shows the generation. It gives information about the substations. You can see which ones have a lot of power flowing through them, but not much generation. Those are the yellow ones. The way we set this up is each one of those rectangles is a GDV. So you do have the ability to dynamically click on it and see its dialogue and get more information about it. One of the newer techniques that we've been working on is GDV grouping. A lot of times in a power system, there's just too many individual objects, so they need to be grouped. We've used this in the industry for generations. A lot of times when you get a case, it's grouped into areas, zones. Sometimes buses are grouped into substations. Sometimes they're grouped by owner. The idea of GDV grouping objects, or what we call GDV summary objects, or GSOs, is we allow this to be done at the one line level, and that allows objects to be grouped in lots of different ways. So you can set the bus groupings however you want. Once you group objects and you are looking at an attribute from the objects, you have to think about what sort of attribute do I want? If I group a bunch of generators together, the attribute I might want is the sum of their megawatt output. So I'd be looking at a sum. If I group a bunch of buses together and I'm looking at their voltage magnitude, maybe I want their average voltage magnitude, but maybe I want the minimum voltage magnitude. So you have to be able to specify what sort of summary attributes you would like. This slide here is an example where I took the Texas, the newer 7,000 bus model. So it's got 7,000 buses. I dynamically grouped the buses by, I put a lat-lon grid on, a latitude longitude grid on there. It's a 10 by 10 grid. And then I put a GDV summary object, a GSO, and I color it based upon what its voltage, minimum voltage is. And then I think I dynamically sized it. I sized it based on how much generation is in that location, the grid. And again, you can use all sorts of different metrics in setting these up. This is a pure 10 by 10 grid where the GDV is located in the grid center. An alternative which avoids having GDVs or GSOs sitting in the middle of the ocean is to, again, use the same sort of grid approach, but put the GDV based upon the average of the elements in that grid. So if your grid goes out into the ocean, obviously your buses aren't in the ocean, so your GDV is sort of moved more towards the shore. So this is kind of the preferred way, although I do like the regularness of this just purely grid approach. So both are available. We set it up so you can easily change the size of the grid. This is where I went from the 10 by 10 to a 15 by 15, and I kept the same sizing, so it allows comparisons. probably with this approach, you would take a system and you'd figure out what grid works best for your system and then just stick with that. What we found is that this is a very effective way for showing multiple types of data. For example, I was recently doing a dynamic stability simulation on the 7,000 bus system, and I wanted to see how the frequency was varying relative to the change in voltage. So what I did is I put a GSO grid on where the size of the grid element, the yellow here, is based upon how much the voltage is deviated from the pre-contingent value at that point in the dynamic simulation. And this is, I guess I covered up the time, but this is at about 3.25 seconds in the simulation. And then I put a contour using GDV substation objects in the background, and I showed the frequency. I guess it's not the actual, it's what I showed is the actual frequency. And this combines how is the frequency varying with how is the voltage magnitude varying. And what we commonly do is set up movies of this so that we can show the results in an animated sense. Okay, kind of moving towards the end. We also are very concerned about visualizing transmission system flows. A lot of the previous techniques work well with bus values, but they don't work well with flow values. For example, if I took that image of the 82K grid on the left and asked you, what's the flow pattern in this? It would be very hard for you to figure that out. So what we're developing are, or what I'm going to present here are some techniques we've developed for interactively visualizing the flow through systems. Now, this is something that has been done for decades with looking at primarily area-to-area interface flows. That's picture on the right is a visualization that was presented at a conference in Switzerland in 1998. That's showing for an Eastern Interconnect model how the power is flowing between the different operating areas. So the idea of using aggregation for transmission flows isn't new. What's new is that we're using now a Delaunay-based approach, or at least optionally a Delaunay-based approach. By using the Delaunay-based approach, what we do is we can take our network and transfer it into a planar graph. Planar graph is one where lines are not going to be overlapping, and then we visualize the flow through the grid with no overlapping lines. So the image on the left with this algorithm is transformed to the image on the right. The image on the right, in this case, I'm visualizing using the areas in the grid, or areas in the electric grid, but we could also set up a GSO mapping, and I'll show you that in just a second to do this. This is based on a paper that we presented at the Kansas Power and Energy Conference 2 months ago. The algorithm is very fast. It's actually a relatively simple algorithm. What you do is you take a system with n buses, 82,000 in this case. You figure out how many bus groups you want. That could be based on a grid. It could be based on the areas. M is the number of bus groups. B is the number of branches. In this case, it might be 100,000 or so. And then you do a Delaunay triangulation of the M bus groups, and that creates a set of segments joining the Delaunay, the really bus groups along the Delaunay triangles. So you have a set of segments. There's S segments. And then for each branch, what we need to do is quickly map it into a segment path. So if a branch goes between a bus in one group, let's say M1, to another group M2, and they're directly connected, then it's pretty easy to know how to map that flow. If the bus, the M1 and the M2 are not directly connected, then we need to know, well, what path do we map that flow to? What the algorithm does is pretty quickly calculate that out. And this is a simple example that I took from that KPEC paper where I took a 7-bus system and I divided it into 5 bus groups, and then I mapped the flows for all the transmission lines here into the different bus groups. Computing the path between the 2 groups is, in general, it's kind of a tricky calculation. However, if you're doing a Delaunay triangulation first, then it is actually something that can be done very quickly. This path calculation is something that is used all over the place because it's something that, you know, is used in routing. But usually when you're using it in that sense, you're trying to route around obstacles. Here with the Delaunay triangulation, we don't have obstacles, so there are very fast algorithms to do this. The challenge here isn't to do it. There are algorithms to do it. The challenge is to do it fast. Luckily, there are algorithms that are extremely fast, and that allows us to do this in an interactive sense. We use something called the greedy routing algorithm, which is very simple to code. With that, here's an example where I took a 500 bus synthetic grid. The image on the bottom left is the actual system with 500 buses showing all the transmission line flows. And then I use flow arrows to show how the power is flowing. And you kind of get a feel for what's going on the grid, but it gets messy because lines are overlapping one another. You know, and that's how the real grid is, but maybe you want to get a feel for what's the overall flow in the system. The image on the upper right shows the algorithm where I did it at a substation level. So rather than having 500 buses, I set it up so I have I guess I had 208 substations. You know, it's still kind of complicated, but now because of the algorithm, using a planar layout, there's no overlapping branches, so you get a better feel for the flow. And then on the bottom right, I used 28. I just put a grid on it, so I had, in this case, 28 groups. And now you can kind of see very well how the power is flowing through that system. This is something that, because the algorithm is so fast, you can take a system with 100,000 transmission lines in it and do this in well under a second. I mean, computationally, there's really not much to this. I mean, you have to do the Delaunay triangulation, but that just depends upon the number of bus groups that you have. And usually your bus groups are going to be several hundred at most. Here's an example. The image on the left shows the Delaunay triangulation of my bus groups. Then the image on the right shows a visualization of how power is flowing through the system. The Delaunay triangulation is going to put lines through the you know, the convex hull. So we've got one going across the Gulf of Mexico, but there's no power flowing on that. So I just eliminate the ones that don't have any power flow on them. And suddenly I can see the flow patterns on this system very readily. And I can do it on any size grid that I want. Here's an example of a 10 by 16 grid. And we've got it set up so that you can like quickly go and change the grid around. The layout algorithm is fast, again, under a second. So you can dynamically do this. Here, what I did is I put the flow pattern on a grid, and then each one of those rectangles is a GSO. So I colored the GSO based upon the voltage or the minimum voltage level there. So you can kind of see where the voltage is low. In this case, the lowest voltage I think is in North Carolina. And, you know, you can, I guess I sized them based on, I think, generation in the area. This is an example of a PTDF visualization for power transfer between Maine and Washington State. Of course, nobody's going to transfer power between Maine and Washington State, but we wanted to see how it would visualize. This is for the 82K grid where we joined the West and the East. Texas is separate. So you can kind of see how power flows through the system. I will say on this particular image, when I was looking at it, I noticed that there was a problem. And you know, with just seeing it on a computer screen like this, you're probably not going to see the problem with it. But if you look at East Texas, right on the East Texas, Louisiana border, and it's kind of hard to see because they've got the white boxes which are showing the actual flow PTDF on the segment, but there's flow going into East Texas and not coming out. So the PTDFs go into East Texas, and I was like, that can't be because there's no change in generation there. It turned out that I was seeing a very subtle bug in the algorithm that we have since fixed, but it's kind of amazed me. I could take all this data and immediately that bug jumped out at me because I was looking at the flow pattern and was very surprised by that East Texas occurrence. This is something that we use a lot of for our geomagnetic disturbance analysis, or some of the studies we're doing now are looking at the impact of high altitude electromagnetic pulses on the grid. And we want to look at how the geomagnetically induced currents, or the GICs, flow in the grid. This can quickly summarize the flow of GICs through the system. Here I took the 82,000 bus system and I applied a geomagnetically induced electric field that had a north-south orientation. The brown arrows show how the GICs are flowing in the system. You can kind of see a flow from north to south there. And then the GSOs, the rectangles, are colored based upon whether GICs are coming out of the ground or going into the ground. If they're coming out of the ground, they're yellow. If they're going into the ground, they're magenta. You can kind of see very quickly what is going on at an overall level. Of course, if you want to delve into the details, you can get details on each one of these, or you could use a full one line. It would just get very complicated to show full sense. One other application of this approach is turns out you can combine different types of data pretty effectively. This is one where we wanted to visualize what was going on with the stability studies, and we wanted to know where were the areas of low voltage relative to how the flows were changing in the system as the stability run was progressing. So what we did is we put a contour in the background using the substation GDVs to show the change in voltage. And then we put the GSOs, the rectangles, and sized them based on the change in generation at that particular point in time. And then the lines show the change in the power flow through the system. So you can see in this particular study, we were doing a double Palo Verde fault. This is a synthetic grid, so there's no CEII here. We were doing a double Palo Verde fault, and so you see the loss of generation in the Arizona area. The yellow is showing how that power is getting made up throughout the grid. And then what you're seeing is we're getting some low voltages and at least some voltage drop in New Mexico because of how the power is flowing through our grid. That's just a part of the grid, the synthetic grid, that's not well connected. So we're getting a power drop there. And actually, it's kind of hard to see, but there's magenta there in New Mexico, which is indicating the generation in New Mexico is actually going down. And that's because the voltages at that part of the system are so low, it's depressing the voltage. You'll also notice the generators in North Dakota are absorbing power for this event. And I won't tell you why, because that's not the purpose for this study. And actually, I think this was just a particular point in the oscillation where they had oscillated low. So I don't think that was persistently low. The point of the visualization is you immediately see that. You see data for an 82,000 bus system with thousands of generators, and we're making sense of what the response of the system is doing. So we're taking all that data and kind of going through the process of giving you insight into what the overall behavior is. And again, the idea is to use drill down so that you can get the details as appropriate. I'm going to finish up just with a little on time varying data. You know, anything you do at a snapshot level, usually in power systems, we want to also do over time. Lots of different ways to do this in the power industry. If you look at control center pictures from generations back, what you'll usually see is a lot of strip charts on the wall. And that's because as power engineers, we have used strip charts for a long time to show the variation in the electric grid. And a strip chart is a great way to do that. So when you want to show time varying data, you could use a tabular display, something we commonly do, where we'll show on the y-axis the time points, and on the x-axis the different values such as bus voltages. Maybe we'll plot it, you know, to produce a time-based graph, which is what a strip chart is in real time. And sometimes we'll set up animation loops. And then recently we've been doing a lot of data analysis algorithms, clustering, using modal analysis to get more insight. Animation loops is something that we use a lot of if we want to convey what goes on in a study. The motivation for this was actually way back 20 years ago, sitting in a utility control room, and we were talking about how to visualize power system data, and the weather channels playing in the background with the animation loop of the radar. And we're like, yeah, we should do that with the electric grid data. So that's something that we very effectively use. This is kind of under the hood of what's going on with these contour visualizations. What we do is we'll put thousands, in this case 40,000 substation GDVs on the one line, and then we'll shrink their size so they're very small, and they become our contour data points. This is for actually the 80,000 bus grid where we didn't have Texas included. We can then visualize what I've shown, like frequency variation. This shows one where we were using a Delaunay contour because they're fast, and visualizing the change in frequency variation for stability study. This is just a different point in that study. This is one where we're showing the voltage magnitude variation, something that I've already shown. These images were before we had the GSOs, the Geographic Data View Summary Objects, and the GSO line summary objects. With those, now we typically will combine a contour with a visualization of some other data quantity. For example, this is going to show how we make a movie up for the disturbance I showed you, the double Palo Verde fault. This would be pre-fault, and then you put the fault on, and at what would it be, 3 cycles later, you see this is how the voltages are changing and how the flows are changing and the generation is changing. That's 6 cycles later. And then you'd continue out and you just string them together. And we've got movies, and you can show the movie. You know, the challenge with the movies is the size of the files gets relatively large as you try to have high resolution images, high time precision, and long time variation. But a lot of times when we make up these movies, what we'll do is we'll use a nonlinear time mapping such that for the first couple seconds, we might show time slower than real time. And then as we start looking at the response over time where things are changing much less quickly, we'll speed time up and show it much more quicker. Last slides are modal analysis. We've been doing a lot of modal analysis to get damping, and that was something that we looked at on this SPP study. How did it impact the damping on the system? How did it impact the modes? We wanted to visualize the change in the modes. So this shows for our synthetic grid how a mode is impacted by interconnecting the grids. On this one, what we did is we took the results from the stability study, and then we did modal analysis, and we've got techniques, something that we call the iterative matrix pencil method, which is very fast at calculating all the participation in the mode. And then we visualize this. This is a GDV visualization. What we did is we put a grid on here, and each one of the arrows then shows the value in that grid. if I showed all of the substations, and again, we've got like 40,000 substations. When we first made these up and we showed 40,000 arrows, it looked like a mess. So we're going more with a grid approach to make things a little easier to see. So that's it. We're done a little early. I wanted to leave some time for question here. Conclusion, there's a lot of data out there. We need a lot of algorithms for studying that data, simulation algorithms, power flows, stability studies, things like that. But we also need to think about then, how do we actually interpret the results of these studies? And that's what this presentation has focused on. It's an area for continued research, of course. And I will say the synthetic power grids help us a lot. We've got them now with dynamics that allow us to present data without being concerned about CEII and make it available. Here's a couple of our recent papers in the area. We've got great admin people here at Texas A&M that have added, and students, because they tell the students to, or ask the students to put up pre-publication copies of the papers. So if you want any of those, and you don't have access to IEEE Explorer, the pre-publication copies are available there. And the papers and these slides are available at the website as well. So I guess I can take questions. Thank you.